Hamiltonian shapes. It's one path that hits everything, no collisions. So it has to be a path that does not hit itself in 3D. Then you can follow these gadgets in order to make any turns you need to do. Or you can go straight. Everything is possible. I'll talk a little bit more about that in a moment. So 2x2x2 refinement, meaning scaling everything by a factor of 2, allows the zigzag to make any Hamiltonian shape, scaled by 2. But that's Hamiltonian shapes. Now, conveniently, there's this theorem which is used a lot in computational geometry, and we use it in this hardness proof, that if you take any shape and you refine it by 2x2x2, you scale by a factor of 2, then it becomes Hamiltonian by a similar kind of gadget construction, although it's easier. If you just want Hamiltonian paths, you don't care about where you're turning and where you're not turning. So that's a pretty easy proof. Left as an exercise to you. And sort of an aside from this issue. So we take any shape, we 2x2x2 refine it, we make it Hamiltonian, then we 2x2 refine it again, total 4x4x4 refinement, and then zigzag path can make that polycube shape. Or any polycube. So that's cool. Now, I'll mention here in this proof one of the issues, which we'll see a bunch of times. I'm just going to mention it here. Is we have a parity issue because the cubical grid is too colorable. Right? You can checkerboard the 3D grid squares. And so what that means is every time you go from one cube on the grid to another cube on the grid, you're switching parities. It's checkerboard 3D space, black and white. There's going from white to black, then black to white, then black to white, then alternating black and white. And easier to do than to say. And so that's a constraint. For example, it is impossible to, in a 2x2x2 thing, to enter from this cube, the front cube, and exit from this one, just by a counting argument. So you start, let's say this is a black cube, this one also a black cube, and so you start black, and then you alternate black, white, and there's 8 things to visit. You want to end black, that's not possible. You have to end white. So if you enter on a black cube, you will leave on a white cube, and if you enter on a white cube, you leave on a black cube. So that's a constraint. Doesn't really get in the way here, but it's something you have to keep track of, and the theorem wouldn't be... What you'd like to say is, well, I can enter from any cube and leave from any cube. And you could actually prove that by induction, except the base case is wrong. So this is something to be careful about. This is the base case. This is one cube. Can I enter from anywhere? One 2x2x2 supercube. Can I enter anywhere? Leave anywhere? The answer is no, but I can enter and exit anywhere that have the right parity. So if the entrance cube and the exit cubes have opposite parity, then this is actually all of the cases. These 4 entrance and exit cube are adjacent to each other, and these 2 cases are where they're opposite from each other, not touching. And that's all the cases with all the rotations and reflections. So once you prove that, the base case is actually really easy to do by induction. You just are essentially pasting all of these things together to make any path. And then we can make any Hamiltonian shapes. Then further refinement, any shape becomes Hamiltonian. So that's how we prove zigzags are universal. And this connects together all of these gadgets. There's really 2 gadgets in this proof. The AI gadgets, there's n copies of that. And the zigzag gadget, there's n copies of that as well. Now there are some details to check here, of course, that the zigzag gadgets can actually navigate around, not cross each other with height 8. And then at the end you can fill all the blank space. If you're just organized about how you traverse each of the AIs and where you put the blank space, I think we just leave some headroom. So you can just go up, walk over to where all the blank space is, just sort of do a scan line traversal. Wherever there's blank space, you eat it up with your zigzag at the end. So all what this does is it lets the AIs move around completely freely. There shouldn't be any constraints on how the AIs are assigned to these pockets. We want every solution to the 3 partition elements to work here. And zigzags let us do that because they're so universal. Cool? So that's what I wanted to say about this proof. Double check my notes. There was one other thing which I found a little funny rereading this paper, is why 8? Because we know everything has to scale up by a factor of 4, but and that's all we're doing in some sense. But we do make these we scale all the AIs by a factor of 8. Not a big deal, but there's a reason for 8. If we just did 4 and say so we want to go. So this thing gets mapped onto here, and we go out and back and out and back. If we just did it 4 times, we'd be arriving at basically the same position in the 4x4x4 block. That's right, we would be arriving at the same 4x4x4 block that we started from. That's not good because we can only visit a block once. So this is sort of an interface issue between the zigzag, which is nice and universal. You can always paste 2 of these chains together, no problem. Whereas with this thing, which is not universal, it folds into basically the shape. That's it. So we need to make sure that, I mean, we can universally do whatever we want in here, but we need to make sure that when we connect between the zigzag structure and then we paste in one of these and then we come back, that we do that in a valid way from the perspective of this big chunk. So the factor of 8 makes sure that we leave from one 4x4x4 chunk to come back on a different one, and then it's easy to paste all the time together. So that is MPath, yeah.
So I don't quite see that this proves that same cube is empty.
Right, yeah, there's one more issue, which is this was folding this shape, but we want to fold it cube. Yeah, this is an annoying part of the proof. It's very hard to draw. This is my attempt at drawing it, and so I will sketch the idea. I'll tell you the first part is conceptually easy, again hard to draw. The issue is forcing this chain of blocks to do anything. And one key idea is if you want to fold, let's say, a k by k by k box, if you have a straight path of length k, there aren't very many places you can put that. I mean, I guess there are still orders k squared of them, but you have to start and end at the beginning and end of the overall cube. You have a full length straight. So the first thing